Alright, so I'm going to be answering your question here about why we think this is not working. Undoubtedly, the reason this isn't working once you rotate the model is the points that you're choosing are creating some axes relative to your model. But the operators that you're using here are rotating around the world X, Y, and Z axis. So they're really, the angles and things you've calculated are correct, but the utilization of them, they don't correspond to these axes. But I'm going to show you a completely different, better way to handle this that'll be more difficult at first, but much easier when you want to do things like this in the future. Okay, so the first thing I need you to do is read this website, or this web page here. The question's not so much important as this answer here. This is just a really great breakdown of the 4x4 transformation matrix. Okay, and that 4x4 transformation matrix is something that is super powerful and way easier to use than trying to use Blender operators to simulate a translation, a rotation, or a scale. So we can pre-calculate all the things that we want and then assemble them into a transformation matrix. Or if we know an object transformation matrix, we can use some built-in Blender tools to decompose it into a location, a rotation, and a scale. Alright, the next thing I need you to watch or brush up on is the cross product. So this is kind of a meaningless page if you're not into the math, and this is a much more important visual description of what the cross product is. So this video will give you enough, and between this video and this answer here, we should be able to accomplish what you want to accomplish. Alright, so here I have this plane called reference points where I just simulated the user clicking in 3 spots, and the vertexes are 0, 1, and 2. I've drawn their indices, in grease pencil so that this makes sense here. Right? So this is just getting reference to the Blender object, then to its vertices, then to its 4x4 transformation matrix. And here we take the coordinate of each vertex. Now coordinates are stored in the local space of this object, so relative to its own origin. And to put them in world space, we need to multiply by the matrix world. Okay, so left molar, right molar, and anterior are the 3 points, and I'll leave it up to you to insert your data here. Because after this point, after this line in the code, you should be able to adapt the input to it to get the result that you want. So we're going to take the midpoint as the midpoint between the 2 molars. We could also instead take it as the midpoint of all 3 points. And I want you to notice here that these are 3 vectors, so left molar really looks like this. Some value, and with 3 different values stored at the index locations. So in your example that you posted, you kind of split all those up into their individual points and then average them. You don't have to do quite all that difficult of a work if you're using the vector, in which you can do just add the vectors together and then multiply them times a third or half, and it will do that component-wise addition and division for you. So that's a tip there. So this gives us our middle point right here between the molars. And now we want to define a vector that represents the forward direction, or pointing out the anterior of the teeth. So we will take that as from the anterior point to the midpoint. So that's going to look something like this. Right, so that will be our forward vector. And then the next thing, and because all of these points that we've calculated are in the same plane, the next thing we want is the up vector. And we're going to get that by using the cross product of this vector here and this vector here. Okay, now if you remember from the cross product video, cross product is always perpendicular to the two vectors that you use to create it. So we could use this vector cross this vector, that would give us the z-axis. This vector cross this vector, or this vector cross that vector. Did I do that right? Yes. So notice that all these, when we go around the plane here, all these arrows are pointing counterclockwise, representing a counterclockwise rotation around the point that we're calculating the cross product on. Okay. So once we do that, so here's the first vector, here's the second one, and then we calculate the up vector using the cross product. So now we have two orthogonal vectors, the forward vector and the up vector here, which Blender will display that in edit mode with this little tool right there. And now all we need is the final vector representing right to left. Now you may be tempted to say, well, that's just the first one that we used here. But there's no guarantee based on how the user drew these points that this will be perfectly perpendicular to that. So instead of using this, we're going to recalculate right using the same feature of the cross product by essentially crossing the y-axis with the z-axis. Okay, so x, y, z will always stay in that order in a right-handed coordinate system. So x cross y equals z, y cross z equals x, and z cross x equals y. So we already have y and z. So y cross z equals x. So that's how we end up getting our third orthogonal vector. Okay, so now we're going to go back to the world matrix concept, and if you remember, we can compose a full transformation matrix from three individual components: a translation component, a rotation component, and a scale component. And the order which we combine them by multiplying them together does matter. But a trick is that for a rotation matrix, the columns of a pure rotation matrix are the vectors which represent the aligned x, y, and z axes with that rotation. Now, you might have to digest that for a second, but what I've done here is just set our x-axis, our y-axis, and our z-axis to the columns of this matrix, and this just creates a blank identity matrix for us. Now we're going to restructure that matrix as 4 by 4 just by adding a row and a column and with a 1 at the bottom. So when you look at this in the console, it'll be a 4 by 4 matrix. We're going to build a translation matrix with this convenient tool that's built in. We could also do the same thing here by setting the final rightmost column to the translation, okay, which is the middle point. And the reason this location is also a translation is it really represents the translation from the origin to the midpoint that we want. So once we've done all of that, we're going to take our visual plane, which I've just put somewhere random, move it to the midpoint, and well, first we're going to rotate it to be aligned with those three axes that we calculated, and then we're going to move it to the midpoint. Remember, these get applied from right to left, so the rotation happens first, the translation happens last. If we translated first and then rotated, it would rotate around the origin, so it would end up spinning in a big arc. Anyway, here it goes. Boom. Easy as that. Okay, so I'll post this blend file and this video in the forum, and hopefully that gives you a lot to go on.